Okay, good afternoon. I'm Dr. Hines. I'm the Nuclear Engineering Department Ed here at the University of Tennessee's Nuclear Engineering Department. Welcome to our Colloquium series. Today we're lucky to have Dr. Zaijing Sun. He's an assistant professor in nuclear engineering at South Carolina State University. He earned his PhD in applied physics and radiation science and accelerator applications from Idaho State University in 2012. Before joining South Carolina State University, he was a postdoc in the Nuclear Engineering Division at Argonne National Laboratory. His research interests include nuclear activation analysis, health physics, environmental toxicology, radiochemistry, gamma-ray spectroscopy, Monte Carlo simulations, and temporal data mining in nuclear engineering. Welcome, Dr. Sun.
Thank you. It's my honor to go to Knoxville and give a seminar at one of the oldest nuclear engineering programs in the United States. The thing I'm going to talk about is applying nuclear activation analysis, NAA, on agricultural products like coffee, like cotton, like vegetables, and the environmental monitoring. We try to figure out the legacy radioactive material contaminations in the air. I come from the Radiation Data Mining Laboratory in the South Carolina State University. Our lab is very small. We only have 3 faculty members, but a lot of students. And we have 3 labs, several HP servers, because we do the computer simulations, and have 1 operation bay, and on top of the radiation detectors, especially we have several germanium detectors, nuclear simulation detectors. And it's a unique state-of-art teaching and research facility operated by the nuclear engineering program at SC State University. And we are the only undergraduate ABED accredited undergraduate nuclear engineering program in South Carolina. And it serves as a principal investigation conduit in the permitted states for research and development in nuclear applications. And I just show you some pictures. This is Dr. Chang working with the alpha detectors, nuclear simulation counters. And this is my 2 students working with the high purity germanium detectors, and we are making the cotton seed spectrums. And this is another student working with the high purity germanium detectors. And the picture is not very clear, but actually this girl working in our lab is a very pretty girl. And she attended the Miss USA competition, and in 2017 her name is Carla Macron. She is the champion. Okay, this is the outline of my topic. Introduction, I will talk about what is the nuclear activation analysis, the features, why we choose it, the history of nuclear activation analysis. After that, I'm going to talk about the calculations and how we simulated the gamma shell and the neutron spectrums, and spectrum analysis. Calculation including 2 kinds of methods. One is absolute method. We get the concentration of isotopes from the original parameters. Or we use relative methods. You irradiate the sample with your reference materials. Then we talk about the Monte Carlo simulations with the PA and NA. PA is photon activation analysis, high energy photons. NA is neutron activation analysis. Then we talk about NAS Online. It's a software we designed for calculate the nuclear activation analysis. It's a web-based software. Case 1 is tracing the origin of the coffee with the photon activation analysis method, and why we study the coffee and the experiment and results. Case 2 is a neutron activation analysis case. It's environmental monitoring along the Savannah River. And why we study Savannah River? Because some places is highly contaminated, and our experiment and results. Then I talk about other cases, the project we are conducting, like cotton seeds, the food safety, the organic and inorganic food, the geological and archaeological samples. Finally, the conclusion and future work. Okay. The first, what is the nuclear activation analysis? Nuclear activation analysis is we expect the nuclear reactions happened within the nucleus. And it's an active nuclear assay, and it's a radioanalytical technique. Usually, according to the irradiation sources, we divide it in two kinds. One is a photon activation analysis. It's accelerator-based. We use high energy photon ray, gamma rays, to irradiate sample. Or we use the thermoneutrons. It's reactor-based. We got a reactor and has thermoneutron and epithermoneutrons to irradiate the sample. The famous case of nuclear activation analysis, of course, is this one. This is Napoleon Bonaparte. And rumor said he was poisoned by his British servant. And how to demonstrate that? So the scientists see these hairs of Napoleon Bonaparte, and then we use the neutron activation analysis to analyze the isotopes in that hair. And we find that, from this article, they find that there's a higher concentration of the arsenic, which is poisonous to people, in the Napoleon Bonaparte's hair. So which indirectly proves that he was poisoned by his British servant. And they even can get the plot and which months they give more poison and the next month. So the whole plot can see in this article. Okay, the features of nuclear activation analysis. First is a multi-elemental analysis. We can analyze a large number of elements all at once. For example, we can apply, at this time, we can do 42 elements at one time. With higher accuracy and precision, it's very sensitive. For some of the elements, we can go to ppb level, part per billion. And the sample size is very small, and we only need 1 to 200 milligrams. And minimum sample preparation, no chemical separation needed. Sometimes you're doing chemical separation, you actually introduce some of the contamination. So that's the advantage of it. Another advantage is called long destructiveness, which I put a quote there because I think it's not really long destructive. Yeah, and the nuclear reactions happen there. You met some new elements. But because your sample is very small, for example, if we deal with some artifacts, we only need to drill a very small hole underneath it and got some powders. And people usually do not notice that, so we call it long-destructive. Okay, the history of nuclear activation analysis started with this guy, Havicek. And he published this article, The Action of Neutrons Upon Rare Earth Elements, in 1936. He used the polonium source. Polonium source produced alpha particles, and then beryllium produced neutrons. Neutron activation analysis. And this article is quite famous because of this. He won the Nobel Prize. And in 1965, the semiconductor detector is first introduced, and in the application of gamma ray spectroscopy, the study of the age in the glass. In 1988, Dr. Segbert, my mentor, and he published photon activation analysis, which is in encyclopedia book. And this is Sackbite. And Michael Glasscock of the Moore University Missouri reactor, he also is expert in neutron activation analysis. This is the basic principle. We have a target nucleus, which is stable. And to make it radioactive, we have a gamma, high energy gamma, or neutron coming in. And it becomes a compound nucleus, which is very active, which is red, and then give off alphas, betas, protons, neutrons, and then decay into another one, product nucleus. Product nucleus is still radioactive. It's still in excited states. And it will enter the beta decay, beta plus, beta minus, electron capture, and give off delay gammas. And then into the final nucleus, which is also stable. The thing we are interested in is this delay gammas. Delayed gammas, we will use germanium detectors to get the spectrum with peaks and with accounts. So the idea is simple. You get a spectrum with energy lines and its intensity, how many counts, and we trace back to the product nuclei and what's the length and what's the mounting length, and then trace back again to your target, what's the length and what's the amount. So experimentally is from here to that. And when we're doing calculation to find out which isotope it is, we just go back from spectrum to product to target. So the key question is how to calculate the radioactivity of product nuclei. Product nuclei is in the between of target nuclei and final nuclei. It actually have two processes. One process is growing. You produce a lot of product nuclei. It's growing with 5 sigma square integral, something like this. And another process is decay. When you produce it, it's also decay with the decay constant there. So we get this differential equation, and we solve it with some initial condition like this. You can get the original number of target nuclei equal to this. The original activity is always equal to lambda multiply this, equal to this. Okay, so this is the equations in textbooks. But textbook did not tell you that this is actually for continuous irradiation. These equations come from the nuclear reactor, which is continuous irradiation. How about the pulse irradiation? We use the accelerators. The curve will still looks like this. So go up, the activity go up, and at the end of irradiation, then it's going down. At BC point, we measured. It's generally still look like this, but if you look in details, here, you actually can see that it's go up, go down, go up, go down, go up, go down, because it's a pulse irradiation. It's go up, go down, go up, go down all the time. And this is a typical pulse. So this is a pulse model. You have a time period t, and this is pulse width. And that's its rest time. It's actually pulse width is very, very small. For L-band linear, usually it's microseconds. But here, it's very long. It's 7 times longer than that. For example, the L-band linear at Icahn National Lab, 60 MeV, if it's continuous irradiation about 10 hours, the real uptime added together, pulse together, only 3 minutes. The other time is just rest time. So if you use that equation to calculate, there will be some issues come up. So how to calculate that? We have to adjust that equation. So we suppose that each pulse irradiation is independent and they do not contact with each other. Each pulse is independent. For each pulse, the irradiation in that pulse width is continuous, and it's only Tp. The total number of radionuclei equal to sum of all the radionuclei generated by each pulse. So we calculate each pulse generate nuclei and add them together. So each pulse will generate at the T irradiation end. The first pulse, you only have this. Second pulse, that. Third pulse, you add them together. That's the new equation we derived. And in this new equation, there has pulse period, pulse width, all this kind of stuff. And this is a MATLAB code to derive that equation. You can see that the derivation 1, superimposing of each pulse at moment Ti, or derivation 2, addition to nuclei generate each pulse one by one. We add them together, they are the same result. So this is the experimental activity. We're doing experiment to prove that. That's the theoretical activity. You can see that they are consistent, but theoretical activity is much higher because we use a higher photon flux. And if you do the statistical analysis, you can see that theoretical activity and experimental activity. We pick up 6 reactions. You can see here the R equal to 0.99289, which proves that our new equation is right. So now we have the new equation. At the end of the last pulse, the total number of productive nuclei n total and the corresponding activity are in this equation, which have the pulse width, pulse time, and pulse period. And this thing was published in 2008 with this paper. And actually, this thing will be shown up in the next version of your textbook. I talked with the textbook of the LAWS textbook, the radiation detection and the nuclear measurement, and also Nick, the last name is hard to pronounce. Yeah, he also accepts that. So they also asked me to give a problem for that chapter at the end of that chapter to prove this. So I believe in the future students will hate me because that problem is too difficult to do. Okay, so we have the growth constant is like this. And in this equation, growth constant, the phi and the sigma, cross-sections have some historical data. We always, even it's not complete, but most of them we can find the historic cross-section data. But how to get this phi, the flux, our way is Monto Carlo simulation. And here is a typical Monte Carlo simulation of the photon activation analysis. And the simulation software, we use the Gen 4. And this is the experimental setup. So the electron beam shoot here, gets the electron gamma converter. This is the tantalum converter. And then you have a hardener. It's aluminum block. This is our sample put there. So material include aluminum, tantalum, stainless steel, water, air, vacuum. And we use general particle source instead of general particle gun. In the Gen 4 program, the default setup is general particle gun. But that thing, we changed it into the general particle source because our electrons actually have energy distribution. So they are not the same kind of energy. They actually have energy distribution. For this one, most of them is concentrated around 32 MeV some stuff, but that's a lot below. The physics list, including carbon scattering, gamma convection, photon electron effect, multiple scattering, annihilation, etc., etc. So basically, all the electromagnetic process we included in that. Okay, here is an animation to show that simulation. I hope it can work. Okay, you can see the red one is the electron beam shoot in. And the magenta color here is actually the tantalum target. And all the green ones are photons, high energy photons. Our sample is right here. So this is a typical photon activation analysis simulation. And with computer simulation, you got the photon flux. And here is our activity. In this period, we use a germanium detector to get the spectrum, got a peak. And the peak area, the lead peak area, is related to this activity from this equation. The peak area will be equal to this. It looks complicated, but actually it's quite simple. The thing we are interested in is this, the concentration of the target isotope. The other thing, we can just rearrange it, and you got this. In this equation, this is actually the final equation of photon activation analysis. In this equation, all the red one we can measure. All the green one we can find it at some of the database. The magenta color we can simulate it. So problem solved. So this way is the absolute method. But I call it quasi-absolute method because one of the parameters, flux, is actually simulated. It's not really measured. Okay, how good this quasi-absolute method could be? It's actually not very good. Look here. This is the nuclear reactions. This is the concentration certified from the sample. The list gives the certification values. This is the thing we calculated with the quasi-absolute method. The accuracy. Look here. The best we can go about 10% away. The worst we can go 50% away. So the only thing we can say that it's in the same order of magnitude. And it's systematically lower because our simulation flux is higher, usually, and the cross-section is also higher. So does this mean photon activation absolute method have low value? And how you can apply nuclear activation analysis to the samples? The truth is, in real practice, we are not doing absolute method. We use the relative method. We always irradiate our sample with a reference material. When you have a reference material for X element, you get this. For Y element, you also get this, and you divide them. You get a more complex, a complicated equation, but for the same element, same energy line, same detector, the same irradiation time within the different object, one is your reference, one is your sample, there's a lot of things can just cancel. They are the same. And then your equation becomes simple. In this simple equation, the only thing you do not know is the flux ratio. What's the flux ratio of your sample and reference? We have several ways to deal with it. For example, this is sample, this is reference. I can put it symmetrically in the beam and assume that their ratio is 1:1. Or we can put something before, something after, like nickel foils, and then doing a mathematical mean, average them as the flux in the sample. Or the best method I prefer is called internal monitor method. And we use some of the solution which have a known concentrations, and we put it into sample and reference, which we already know, and then we put it into beam, irradiated. Okay, for internal method, for element X whose concentration sample is unknown, we get this. And then we can say the concentration is equal to this. This thing we do not know, this flux ratio. But this flux ratio can be calculated with internal monitor I, whose concentration is low. For this internal monitor, we get this, and flux ratio equal to this. Then we can put this back to there. So we move this flux ratio away and put the internal monitor ratio there. And then calculate, concentrate some, cancel out the mass, and get final result. So this is a good thing of internal monitor method. You get the ratio of flux, and also the mass is cancelled. You even do not need to measure your sample and reference. Just put it irradiate, because in calculation that we are gone. Okay. This is the equation we used for activation analysis. But this equation, when you're doing the calculation, is still very complicated because each isotope may have different isotopes, and the lambda is different decay constants, the peak area season. So if you calculate it with your hand, it's a painful experience. So what we do is use computer. We have a software called Nuclear Activation Analysis System. This software we designed, but there's an old software which has some issues. It's easy to introduce human error. It's green unfriendly, and set a high bar for using it. Missing counting error propagation, which I hate that. And they designed with some Excel sheet and basic program. That's the old one. The new one, we do it with the SQL, C#, and ASP.NET. It's a web-based calculation system. Basically, we have data server, web server, and your personal computer. Use the web server to contact web browser to contact with the web server with ASP.NET, and then with the open database connection to connect with the SQL. All the calculations is done with this data server. And the data server feedback to the web server, and then you can see it on your personal computer. The data source is the most important thing in this calculation in the NAS system. And we use the WW table of radiated isotopes, and it has 19,000 gammas, different X-rays, because you want to recognize which gammas which is. And the cross-section, we use the X4 database from the experimental nuclear reaction data. We retrieved the data from that. The library, which will tell you what kind of reaction will be happened with the gamma beam or neutron beam, is come from these two books, Photon Activation Analysis Library, this book and this book. Okay, this is one of the algorithms for internal monitor methods. You have sample peak, you have reference peak, and then the isotope library identification is use this lib, and then the flux factors is calculated by this part. The concentration calculation is from this big table, calculation, internal monitor method. Okay, let me show you the program looks like. Hope it can work. It's actually online. Okay, just open your web browser. You can see nas.scsu.edu. And yeah, it's funded by USDA. And you can see the PA and NA. You just go. It needs to create an account there. And right now, it's free to create it. And register. and you uploaded your spectrum file, like soil or coffee or something, and click upload it, publish it into the system, and you can see that all the energy lines, the deviations, the peak area, you can edit them, and then click next. They uploaded another file, like a ppm file, then use the different methods. For example, analysis or internal monitor methods, external monitor method. You can change that. Okay, this is the result come out. So just click it. You can get all the isotopes, the productions. So with this program, and we basically solve all the technical issues in the neutron activation analysis and nuclear activation analysis. So let's see, jump to some cases. The first, coffee. So why study coffee? Not because the coffee tastes good. It's because we want to crack the illegal drug trade route. Look here, this is the illegal drug trade. This is actually a DoD project. They want to find out where the drug comes from. And so we want to test the drugs, like heroin or something. But FDA is against it. You cannot use drugs on campus. So what do? We use coffee to as a surrogate to study the drugs. But look at here, these two pictures. If you can see that a lot of illegal drug here, drug-producing places is actually coffee-producing places. Especially look at the Colombia. Some places produce drugs, and they also produce very good coffees. And actually, I think coffee is a kind of drug, right? And here is the sample we collected. We actually collected sample from some sample is dry coffee beans, some is washed. Some coffee powder has a Swiss water process, some is low Swiss water. That process will produce decaf coffee. And some coffee come from Hawaii, some come from Guatemala, some from Colombia. Okay. And this is the sample in the coffee beans in bags. And this is a grinder. It's a grind coffees into very fine powders. And this is a sample. This is a reference material. We use the fly ash and this standard. Okay, let's shoot it with high energy photon beam. Come from Idaho Accelerator Center. And this is a 44 MeV Santa Barbara NINEC. And this is the radiation detection. We collect the spectrum there. So this is the experimental result. First of all, photon activation is very good to shoot coffee. And in the coffee, it actually can see a lot of elements. For example, here we can see 35 elements in that with very high accuracy and precision. And this is coffee from the same geographic region. This is all Hawaii coffee. These two farms is actually about 7 miles apart. And I visit them. It costs a lot of money. And here is the Hawaii, the Nevada soil and Hawaii soil. Look, the soil is very similar. Coffee is also very similar. But if you compare coffee and soil, it's different. And it turned out, for example, this is tin, and this is thorium, and this is potassium. This is a log scale. They are completely different. That means coffee is a kind of life form. They actually can block some of the elements they do not want and extract some elements they want more. For example, this iron. In the soil, there's a lot of iron. But in the coffee, it's not too much iron in it. And Also, this potassium, which is very important for any life forms, metabolism. The potassium has a lot in the coffee, but not too much in the soil. It's actually extracted. Okay. Could we tell where the coffee comes from? Yes, we can. Look here. And this is the principal component analysis. And this is principal component 1. You can see that there are just 3 different ellipses with 90% ellipses. So they are completely different. And the only thing I'm interested in is this one. Oh, no, this one. This one is right at the edge. This is actually a coffee sample. I get it from the local market, and they say it's come from Colombia. The other sample I know it's come from Colombia because I get it from a professor from Colombia, and they got it from the farm. But this one is questionable, and so it's right at the edge. On this analysis, it's at the edge, but look at here. I have another thing. Hope you can see. And this uses the 3 elements. You can see that one is actually far, far away. See here. So basically, that local center just sell me a wrong one or a fake one. He said it's from Colombia. Okay. So from this case, we learned that coffee from different locations have different concentration of trace element. The matrix of elements in coffee sample are closely related to the matrix of the elements of the local soil. And as a life form, coffee can work like a refining factory. It has the ability to not only increase the concentration of crucial elements in coffee beans, like potassium, but also block some elements like iron, which it does not need. However, the majority of trace element content is similar to that of local soil sample in which the coffee is planted. If suitable elements are selected, it is possible to group the sample from the same geographic origin together. Therefore, it is conceivable that the element content could serve as a fingerprint to tell where the origin of the coffee or where the origin of the drugs. It can tell. Okay. Let's talk another case. The previous case is photon activation analysis. This one is neutron activation analysis. We do environmental monitoring along the Savannah River. Why we study Savannah River? Of course, this is Savannah River. It's right at the edge of Georgia and South Carolina. And here is Aiken, and here is the Leslie Savannah River site. It's because of the Cold War, it was a nuclear bomb plant. It produced hydrogen bomb and other radioactive material. And it's actually the Savannah River region has a lot of animals. To protect these animals and plants, we need to do the environmental monitoring. And this area is also suffering from industry development. For example, Augusta here is actually an industrial area. And you can see this is the local plant there. It's called U.S. Batteries. And Savannah Riverside, of course, it has a lot of garbage, the radioactive, low radioactive waste buried there. So for us, there's an article published, I think last year. It said, Deadly Legacy, Savannah Riverside near Aiken, one of the most contaminated places on Earth. So we need to monitor it, and this is the radionuclide contribution to the air and to the water liquid pathways. And you can see that there's some cesium-137 and also a lot of the tritium. They make the hydrogen bomb. And here is radionuclide contributions from those above this. This see here is from the tritium, and also some plutonium and others. And here is 10-year history of Savannah River, maximum potential at all pathway doses. Okay. The sample. We collect the sample along the Savannah River. The one thing we collect to monitor the air is this Spanish moss. Spanish moss is a very interesting plant. It's just grow in the air. It do not have root. It's just hanging on the trees. So it's a very good bioindicator of the air pollution. And we also collect water samples, and we also collect some sediment from the water. Look here, this is a sediment. Look at this black sand. This is a very interesting black sand. I will tell you later. And here is some of the samples. It's not complete. I just put it here. So basically from Greenville, and we collect hundreds of samples along the Savannah River. The irradiation of neutron activation target was finished with the post-star nuclear reactor at NC State. And you can see the Cherenkov radiation there. And our samples will be put into these 4 tubes and directly to this reactor and irradiated. This is for the long-lived isotopes. For short-lived isotopes, there's 2 tubes here. Look at here. It's kind of like the numerical system in a bank when you try to get some money. And you put a sample there, it will shoot to the reactor, and after 30 seconds, and then get it back. So made short-lived isotopes. This is 2 students prepare the samples. And this is Dr. K helping me to get the sample out. This is the pool of that reactor. And when you finish radiation, it's very high radioactive. You have to put there, cool down about 1 week to get it. That's for long-lived isotopes. This is the part of that numerical system. So you put this, it will shoot to the reactor. And this is another student helping me to work there. This is an automatic sample exchanger. For long-lived isotopes, it needs to be made about an hour. And you have hundreds of samples. So we have this kind of like a robot. And get the sample, made an hour, change another sample to get it. For short-lived isotopes, numerical transfer system, we use it. 20 seconds irradiation. For medium-lived isotopes, it's labor-intensive. Several students work on that. 7 days after irradiation. And long-lived isotopes, we use the automatic sample exchanger. That's about 1 month after irradiation, and measure spectrums. Okay. Now it's the spectrum. This is the spectrum before the irradiation for this sand. And the black sand, you can see a lot of elements in them. And those elements, these peaks, is actually come from the lateral radioactivity decay. This is come from that 3 series. So those black thing is actually more active than your planet. And this is the air, the Spanish moss sample. Before we irradiate, we just put it on the germanium detector to measure it about 1 day, 12 hours. And to see, it's more than 12 hours, to see the radioactivity on that. And here, you can actually see a small peak here. That peak is from cesium 137, which is not later occurred. So we suppose this thing is coming from the nearby Savannah River site. Okay, here is the Spanish moss samples to see the heavy metals on them. And we have 3 categories: the urban low traffic area, like Orangeburg; urban high traffic area, like Savannah, Georgia; and also some rural areas, And you can see that the elements in Spanish moss, low traffic areas, no traffic areas, this is the iron, this is zinc, and this is the corning, and it's barium. Okay, you can see that the traffic-related elements, iron, zinc, zirconium, and barium, are significantly higher in the urban higher traffic area. So in the urban higher traffic area, the Spanish moss grow there. They actually get a lot of heavy metals. They are actually, these things are all coming from your gas. And this is the elements in sediment. And we have Anderson, South Carolina, and Augusta in Georgia after St. Barb Ferry. And there's elements like this nickel, and this is zinc. Okay. What I want to show you that is after St. Barb Ferry. That place is exactly where the U.S. battery is there. And before that, the sediment looks quite clear. But after that, you will see a lot of chromium, zinc, and nickel in that. And this one is for the surface water. We also have Lake Hardware. It's very clean there. Augusta, kind of polluted. Fort Pulaski is near Savannah River. It is close to the Atlantic Ocean. And here you can see a lot of elements difference. For example, this one is from Fort Pulaski. The Augusta have a lot of iron, copper, chromium, zinc. I know it's from the U.S. batteries. And the interesting thing you can see here, the Fort Pulaski, the chloride, and here sodium, sodium and potassium is quite higher. Why the water at Fort Pulaski have a lot of chloride, sodium, and potassium? What? Yes, exactly. That's near the ocean. It actually is kind of seawater now. When we collect sample, it's actually seawater. So from this case, we can learn that some of the sediment samples near Lake Hardware has abnormal lateral radiation due to a mixture of black mineral particles. And they are actually come from the solid rocks into the groundwater. You can see the different series. Spanish moss was confirmed to be a very good monitor of the air pollution. And we can see that difference between the urban traffic size and remote rural areas. The trace element in surface water, and you can see that the difference between Augusta, Georgia to Savannah River, and there's a lot of pollution confirmed from the industrial pollution. But the direct pollution sources need to be pinpointed. We need to do more samples and testing. Okay. This is the case of neutron activation analysis. Our group also doing the other cases. For example, this one, the toxic trace element in cotton seeds. This is a very old picture, dated 1872. And there's black slaves working in the cotton field to pick up the cottons. And the cotton is a very important cash crop in South Carolina, but the cotton take a lot of elements from soil, and that element will go to the cotton seeds, and then grind it into miller to feed the animals, or you get the cotton seeds oil to feed the people. Finally, they all end up into the human table. So any of the heavy metals you get here, finally will end up on the table. And South Carolina is actually rural area, but some of places are actually heavily polluted. This is the EPA priority site. And we actually can a lot of condensates, get a lot of condensates from Davis Station and see the local soil. And this is an article we published at the Hawaii conference. Okay, another case is try to find out what's the difference between the organic and the non-organic food. And this is the project my wife very interested. And the food come from Trader Joe's, Whole Foods, Costco. And some of them, they have said they are very expensive. Organic food typically contains same amount of nutrition, vitamins, and minerals as non-organic food. But organic food contains fewer pesticides, fewer multi-drug-resistant bacteria. On average, organic food is 47% more expensive. And so we collect a lot of samples, vegetables and fruits. And this is the USDA organic label there. And we do it at the NC State to see the heavy metals difference. And there's a paper and going to be prepared for the Journal of Radioanalytical and Nuclear Chemistry. I haven't published yet. That is still under review. But I can tell you the results. And I do not see any difference. Not a big difference. It's just say organic. The heavy metal is very similar. Okay. Here is another case, authentication of the Hertian jade. Hertian jade is famous. It's expensive. And this is the 2008 Olympic medal. This medal has gold, brown, silver in the middle, but this one is actually the jade. The jade is very expensive, so there's a lot of faded jades around the world. And we collect some real ones, real jade, some fake ones from local, and some stones from the local river, and try to tell their difference. They are totally different. And it's very easy to see the peaks of the jade and the peaks of stones are different. And that article was presented at the Cary conference. The last one, I'm going to talk about prevalence study of log sculptures. And there's a small museum on campus. It's an African-American museum. So it has a lot of statues come from West Nigeria, Western Africa. It's about 2,000 years old. And this is another statue. This is a male. And it's from the local culture. Local culture is quite big in Western Nigeria. The area, some of the places produce them, some of the places buried them. And we studied the head, studied the figurine, and studied the soil. They actually have some soil attached to it when they dig it out. So we can see that the soil is completely different with the head and figurine, which means that the figurine and the soil, they come from the same place, but soil is different places, which support the archaeological theory that they are made at one place and then moved to hundreds of miles away and buried underground. And this article was already published at the Journal of Radioanalytical Chemistry. Okay, conclusions. NA and PA is a versatile nuclear technique with high accident precision. It can be applied to study of environmental, biological, geological, agricultural, and archaeological samples. And we derived a level activity equation for pulse irradiation and confirmed with MATLAB and also proved experimentally and will be in the textbook in the future. And we have a web-based spectrum analysis program and user-friendly and can be visited anywhere when internet is available. I can still do calculations when I was in China. It's fine. And with the assistance of Monto Carlo simulations, that's the future work we want to do. And we want to improve the absolute measurement. Right now, it's only in the same order of magnitude. But if we improve the simulations, improve the experimental conditions, maybe we can do it. And maybe we can generate 3D imaging pictures with that technique. So the future of this activated nucleus is very promising. And I would like to thank my students from Radiation Data Mining Laboratory, like Emmanuel, Lafayette, Joshua, Emmanuel, Neutron, Joshua, another Joshua, Kasiga Bishop, Dale, Joan, Jalen, Kingsley, Katisha, Gianni, and Sihan. And also I would like to thank Dr. Forrest from Idaho Accelerator Center and Dr. George Vandegraff of the NIF at the Argonne National Lab. And I would like to thank Dr. Tsai from North Carolina State University. And this research is supported by National Institute of Food and Agriculture, USDA, the MNM project. Thank you.
Couple questions. Questions? Who wants to catch the box?
So what reaction have you gotten so far from the coffee project based upon the results that you've shared from it?
They continue that funding. So I think the next step is try to do some research on the drugs. But coffee as an initial surrogate is quite successful.
Thank you.
Great. Anything else? We're almost out of time here, so let's thank Dr. Sun one more time.